All right, welcome back. We are going to be talking now about triple integrals. And triple integrals are exactly what they sound like. Integrals in 3 dimensions. The only thing that really is different is that we have a couple different coordinate systems that we use. Now, I'm pointing out here there's cylindrical, spherical, and of course I didn't actually give this a name, but this is Cartesian. So let's move this over. So Cartesian coordinates are just exactly what we're used to. X, Y, and Z, dV being dx, dy, dz, or dy, dx, dz, or any combination of them, okay? All right, cylindrical. Cylindrical coordinates are actually basically polar coordinates if you think about it, right? X and Y have the same polar coordinate transformation, and then Z stays itself. So all it is you're just adding Z to the polar coordinates. Okay. Now, spherical coordinates. That's where it starts to get a little interesting. Okay, so, spherical coordinates, this is how it's listed in our book. And I make the note later that every other book that you look at will have these slightly different. I'll say how later, but let's just focus on what our book does for now. Okay, so I've drawn 2 different pictures here. So this is the full 3-dimensional picture. Okay, now in this, rho is the length or the distance to the origin of the point. Okay, so x squared plus y squared plus z squared equals rho squared. So it's just, like I'm saying, the distance from the origin of the point. Okay, here it's from this point to that point. Now, there's a couple angles here. The angle theta. Theta, we actually give it a name. It's called the azimuthal angle. And it's an angle in the xy plane, or angle around the z-axis. And actually, it's actually the same theta that we had in polar and Cartesian or polar and cylindrical coordinates, okay? So that theta is the same thing. Now, we also have this other angle, phi. Okay? Can't remember the name. I'm tempted to think it's polar angle, but I don't have it in front of me right now. But the phi, that's an angle down from the z-axis. Okay, so I'm drawing here in 2 dimensions. This r sort of represents the xy plane. Okay? And actually, if I wanted to say what r was, r is equal to rho sine phi. Okay, so I want you to notice that here you have rho sine phi, rho sine phi. So this thing here, that line there, is that same rho sine phi. Okay? And rho sine phi has a cosine component and a sine component, the x component and the y component. Okay, that's this point here. All right. Now, there are some restrictions on this. Rho is always positive. All right. Theta being the azimuthal angle, that's the angle all the way around here. So that could be anything from 0 to 2 pi. Phi goes down like so. It does not go farther, okay? If it went farther, you'd actually be double counting some things. So phi is restricted from 0 to pi. Okay, think about that object I'm tracing out. If you rotate it around the z-axis from 0 to 2 pi, you get everything. You get a full sphere or ellipsoid. Okay? The integral, the volume element of the integral, a little bit of a complicated expression, but not really. Rho squared, okay, rho squared, sine phi, and then the d rho d phi d theta. Okay, so one of the things to sort of keep in mind is that the sine phi, the way I remember that it's sine of phi and not sine of theta, is that since phi is from 0 to pi, sine of phi has to be greater than or equal to 0. Okay? Sine of theta is not restricted to be strictly positive. So if I put a sine of theta here instead of sine of phi, I could get a zero integral for non-zero stuff, or zero integral for strictly positive things. Okay, so I'm remembering that, no, I need this term to always be positive. Okay? Now, a lot of books write the spherical coordinates a little bit differently. They write it as r phi theta, but what's confusing is that the phi that you see is not the phi that we have here. And the theta that you see is not the theta that you have here. They're actually switched in a lot of books. Okay? All right? So just keep an eye on that if you're reading other sources. And these are just 3 coordinate systems that we have. There are actually a lot of them. There's basically about 11 of them that are used frequently. And as you move forward, you'll see them. So the idea is just sort of let's familiarize ourselves with the tools of different coordinate systems. And we'll use these 3 as examples. Cartesian, cylindrical, and spherical. Okay? All right, I'll be back and we'll start doing some problems.